Okay, so the last piece here about the exponential, one page here. If we were to look at the probability that y is greater than s plus t, given that y is greater than s, assuming both s and t are positive, what would that work out to be? Now, I said in the notes earlier, but I didn't mention it again, is that as far as exponentials are concerned, a lot of things that are measured or modeled by exponentials have to do with time. They're certainly not the only types of models used, but time is a very common thing to be modeled with an exponential. Okay, so anyway, we go back to the definition of conditional probability. We've got y greater than s plus t, intersected with y greater than s. The intersection there is would be y greater than s plus t. So if we go ahead and plug into the greater than case on the previous page, we've got e to the negative quantity s plus t divided by beta, divided by e to the negative s over beta. The s's are going to cancel, or the negative s's are going to cancel. We're left with e to the negative t over beta, which is the probability that y is greater than t. We had something like this with the geometric. It's the memoryless property. And in terms of an application here, an example would be with regard to the checkout. Suppose somebody's been in service for more than 4 minutes, has not completed service yet. What's the probability that it will take more than 6 minutes to complete service? According to the memoryless property, this is basically saying what's the probability that y is greater than 2, the difference between the 6 and 4. And we go ahead and plug back in to the e to the negative y over beta format, and we get that answer right there. Okay, that brings us to the beta distribution. Now, you'll notice the notes for the beta distribution are a little bit shorter. That's because a lot of the stuff that we're doing with the beta distribution uses stuff that's similar to what we did in the case of the gamma distribution, so we don't have to rehash those and just bring it up when it comes into play. Okay, so as far as the beta is concerned, our density is right there. You'll notice the constant is a function of gamma functions. But as far as the kernel is concerned, it's y to the alpha minus 1 times 1 minus y to the beta minus 1, and that our domain is strictly on the open interval from 0 to 1. Again, alpha and beta both have to be positive. There's some important modeling aspects with regard to the beta. One of the neat things about a beta distribution is that by varying the parameters, you can get all different types of shapes. You can get a density that's symmetric, you can get one that's left skewed, you can get one that's right skewed. It turns out that if either of your parameters is less than 1, then the function is going to be concave up, and if they're both greater than 1, the function is going to be concave down. Although I didn't mention it here, if both alpha and beta are 1, then you end up getting a uniform distribution from 0 to 1. So the uniform 0, 1 is a special case of the beta. Okay. The mean and the variance, we've got the derivations, and once again, we're using the kernel similar to what we did in the case of the gamma. And so in the first case, you'll notice that with the y that was brought in for the expected value of y, we end up having a beta kernel again, and the parameters are alpha plus 1 and beta. And so if we go ahead and plug that into the reciprocal of the general form of the constant, remember that's the general form. So what we're going to do is we're going to take the reciprocal of that and we'll replace alpha with alpha plus 1, which was done right there. And then we use rule 2, do some cancellations, and what you end up getting is alpha over alpha plus beta. Again, here's one thing to notice with regard to this. If alpha is the same as beta, not only we said that it's a symmetric distribution, but that expression there will always work out to be a half if alpha and beta are the same. If alpha is greater than beta, then it's going to work out to be more than a half, and if alpha is less than beta, it'll work out to be less than a half. You've got the derivation of the expected value of y squared, and again, you've got an expression right there. I'm not going to take the time to go over it. You can read through that, and then the top of the next page has got the calculation of the variance. I didn't take the time to go through the algebra, but there's the expression for the variance of a beta. Another reason why you're glad that I give you the sheet with these formulas on it instead of making you memorize it. So, okay, so some stuff that we saw similar to what we did with the gamma distribution. First, find the value of the constant for these two betas. Okay, in the first case, remember we've got y is between 0 and 1. We've got y to the fourth, so alpha has to be 5. We've got 1 minus y quantity squared, so beta has to be 3. In the case of b, we've got c times y to the seventh, so alpha's 8. And effectively what's going on there is we have 1 minus y raised to the 0. Well, that's going to be the case when beta is equal to 1. So, as I said before, we got a beta 5,3 and a beta 8,1. If we plug those into the formulas for the constants and cancel on the factorials, we get 105 and 8 respectively. So, to write out the formal density functions, those c's right there would be replaced by 105 in the first case and 8 in the second case. For the values of the mean and the variance, the standard deviation, although I didn't write them, this is basic plug and chug into the formulas that we got. So in the first case, 5/8 and 5 over 192. In the second case, 8 over 9 and 4 over 405. Okay, now, whoops, sorry, time to take a break.